So I guess we should start precisely on time. So it is our immense pleasure to welcome Leslie Kaelbling for this talk at the Reinforcement Learning Virtual School. Leslie is a computer science professor at MIT. She graduated from Stanford University, was previously a professor at Brown University. She also is a major personality in artificial intelligence. Among her numerous and many contributions, which I definitely cannot quote them all, we can quote her interest in partially observable Markov decision processes, in artificial intelligence in embedded systems, in reinforcement learning, of course. Um, she was the founder and the first editor-in-chief of the Journal of Machine Learning Research. She has received numerous and various awards over the course of her career. And if I may end this introduction on a specific note, when we were discussing the talk that Leslie would give at RLVS, she mentioned having a contrarian point of view about the fact that most of the reinforcement learning work going on right now is focused on machine learning that solves very narrowly specialized tasks, and that we should be aiming for much greater generality. And we're really looking forward to having this idea developed. And so, Leslie, thanks a lot for the controversy and for the insights on that matter. We're very happy to have you. The floor is yours.
All right. Thank you very much, Emmanuel, for the invitation and for humoring a contrarian viewpoint. I feel that I earned my right to be a contrarian because my PhD thesis was about reinforcement learning, and I had an actual robot do actual RL during my thesis defense. So I do understand and appreciate RL, but what I'm going to do today is actually talk about how I think it fits into a bigger landscape. And I like questions and argument, and so I don't mind at all. Please ask questions. Um, okay, so what do I want to do? I want to understand fundamentally how we could make a general purpose intelligent robot, so as intelligent as you. And I like to think of one of my examples I like to think about is imagine a robot that could make tea in any kitchen, right? You could probably go to any kitchen in any house in the whole world, and probably they have some way of putting leaves in hot water and making something to drink out of it. And probably you could eventually figure out how to do it. You might not do a great job, but you would figure it out. And you should be able to do any job in a household, like, so be really general. So let's just first think about how we frame this problem, the way I think about the problem. So I think that my problem is to be a robot factory. I want to make robots that can go out into the world and be good at what they do, where they go. And those robots, I'm not going to worry about hardware, so I'm just going to focus on the software. And those robots are going to have a policy in their head. Their policy is a mapping from the history of observations and actions into the next action. So it's hard to argue with that as a setting that covers basically any kind of computer program that interacts with the world. But the way I want to think about the spec for my robots is that given a distribution over possible worlds that they're supposed to work in, right? Like, so maybe they're supposed to be able to work in anybody's house or in any factory, or maybe they're just supposed to work in one particular factory, right? So the distribution could be broad or narrow. But given a distribution over sort of problems or worlds or domains in which the robots are supposed to exist, I would like this program that I put in the robot's head to perform well in some expected value sense. The details of exactly what this formula is don't matter too much. So, okay, so this is the way I think about the problem that I have to solve at the technical level. And one of the reasons why I always stop and kind of do this framework to start is I think what's good about it is that given a spec, given a distribution over the problems that the robot should solve in its world, there is an optimal policy. And I think what that means is that we don't need to argue about methodology in a sense, right? It's going to learn what it needs to learn, and it's going to have built into it what is known, what is static about the environment it has to work in. So there is, given a domain distribution, there is an optimal strategy for the robot. But the difficulty now, in a sense, is that the problem of the engineers who are making the robot factory, is to go from a domain distribution description, which is already hard to arrive at, and figure out what program we should put in our robot's head. So probably most of us are in some way or another engaged in this problem. Although I think sometimes reinforcement learning people think about what the robot should be doing when it's in the world, and sometimes they think about the factory problem. And I'm going to kind of circle around about that because I think it's important to keep them separate. Okay, so another thing I like to do is to try to think about a kind of a space of in which you could see that problem that we talked about. In one dimension, there's just kind of the complexity of the problem the robot's going to have to solve, from some very narrow and specific task to some very broad range of problems in a broad range of circumstances. So that's my x-axis here. And the y-axis here is like, what do we, the engineers, know about the domain in advance before the robot goes out into the world? So you can think of this, my y-axis, as being kind of like the variance of the problems that the agent's going to have to solve. So there's all these different kind of points in this space. And for different points in this space, I think we'll want different strategies and methodologies. Okay, so how do we think about finding a good policy given a distribution over domains? And I think fundamentally, just again, from an engineering perspective, well, we have to pick a good model class and a good way of finding the models, whatever they'll be. And I think what we should think about is minimizing the total construction cost. That is to say, how much time do the engineers have to spend writing down a model, building a simulator, doing reward shaping, gathering data, all that stuff, whatever it is. I think it's completely interchangeable. It's not more or less virtuous to write down knowledge or to build a simulator. That's just all engineering activity. And then there's work, again, offline work in the factory, work that computers have to do, like optimizing or running machine learning algorithms or doing meta parameter tuning or that kind of stuff. And it seems to me that we should just try to find a sweet spot as engineers, pick a kind of a way of a model class where humans have good insight, that the engineers can be effective, where we can do optimization, where learning will generalize well. Okay, so we could think about different ways of representing policies. And I know that talking to this audience, you know everything about how to represent policies. So I'm just going to buzz through this, right? So you can represent a policy as a policy. So a thing that the engineers could try to do is to just straight up try to find a mapping from observations to actions and to think about it that way. Okay, and we know how to do policy search offline to look for a policy. But sometimes finding policies is hard, especially if you want to have a long horizon. So then we say, oh, well, maybe we should do it in terms of a value function. Maybe it's easier to organize that algorithmically. And that's fine. I'm going to argue that maybe this isn't the best strategy for representing policies in very complicated domains. I think when we think about using value functions as our inherent representation of a strategy, implicitly what we're doing is we're relying on dynamic programming. We're saying, oh, dynamic programming is awesome because you can reuse the solutions to subproblems. But if you're operating in a domain where you are unlikely as an individual to visit even a small fraction of the state space, of the possible state space, then I would argue that a Q function that's defined over the whole state space might not be the best representation. So for instance, I could go to your house and figure out how to make tea once I was there and I started to get the stimuli, but I would have to look around and I would have to ponder and I would have to think about how you make water hot in your kitchen and where you keep the stuff. And I surely have not pre-compiled a reaction to every stimulus sequence that I could have that would involve being in your kitchen and making tea. So I just don't think that that's a sensible way to approach that problem. So I'm maybe more inclined to think that saving some reasoning to do online might be better for generalization, right? Maybe if we knew some kind of transition and reward model, and maybe some, some approximate policies or queue functions to kind of help with the search control in some places, that might give me a somewhat more generalizable way of interacting in the world. I'm going to argue that planning is good, but doing it at the raw input and action level is probably not so good. So I'm going to build up toward a somewhat more complicated story where maybe we can have some, and generally there will be state in here, something that takes sequences of observations and builds some kind of a state representation or even a distribution over states at some maybe higher level of abstraction that might be more amenable for doing planning. So I think planning in images is not a sensible thing to do, for instance. And then maybe I can make plans, and maybe my plans now are not, again, I'm not outputting torques. Maybe I'm outputting a kind of a more abstract notion of an action that I give to a controller, which might actually execute that in the world. And eventually I'm going to tell a story that involves some kind of hierarchicalization too, so that I can solve longer horizon problems. So these are all ways to represent a policy. Notice that the interface between this big blue box and the world hasn't changed. It's still a mapping from observations and actions, histories of observations and actions into actions. It's just that I, as the engineer, I'm thinking about imposing some structure on that thing to help me engineer it. Okay, so how can we get a policy? So classical engineering, right? So there's a beautiful history, and Atlas can do this great parkour, and that's awesome. Generally speaking, it's good for solving problems where the problem is relatively well known and not so broad, but awesome. There's this other thing, which I think is really interesting, and I'm going to do a little like a detour about. So take this, learning to manipulate an object in the hand, which was a kind of an amazing thing. So, but I would argue that it still occupies the lower left-hand corner here, in the sense that it's a very narrow problem, right? Rotating a Rubik's Cube is a very particular thing. That's what that robot can do, and not too much more, or anything more. And furthermore, there was not very much uncertainty about this problem in the factory. Like, they knew totally what this robot was going to have to do. But yet somehow they used a machine learning approach. So what does that make any sense at all? And so I want to just look at that for 1 minute. So I want to think about what's going on. And I think of this as reinforcement learning in the factory, right? So this robot didn't do any learning online in the wild, right? All the learning was in the factory. They made a policy, and then the policy went into the robot and it did what it did. And so the way this works is you say, well, okay, I understand the world that my robot is supposed to work in pretty well. In their case, there was some uncertainty, right? And there was a lot of work about domain randomization and so on. But roughly, I understand the world that my robot is supposed to work in. But I don't know a way of converting my description of the domain into a policy directly using any kind of classical or analytical methods. So instead, what I do is I think of it as a compiler. I think of it as saying, all right, I'm going to take my simulator and plus a reward function, and I'm going to hook it up to a reinforcement learning algorithm. And it's going to run, this is just computation. It's not learning in an information theoretic sense, because all the information we had about the domain is encoded in the simulator. But we're going to run a computation for a long, long time. And eventually out is going to pop a value function or a policy. And then that value function or policy that pops out, I can hook it up to the world, and then it can behave. So that is and I think almost all the RL work that's going on right now roughly operates in this regime. And I want to make an argument about how to evaluate this I think it's a worthy thing. I have no trouble with it at all. But I want to make a couple of points. One is, it makes no difference whatsoever how much reward the agent gets while it's learning, because it's just learning in a simulator. That's what matters, and it doesn't matter how many trials it has or anything. That really, the only thing that matters is, as a function, because it's a compiler, as a function of computation time, how good is the policy that pops out at the end? Okay, so if there's any conversation about this, I'd be happy to take a question, because sometimes people don't love this part of the story.
Well, maybe to clarify,
Mhm.
when you're writing value of current best policy, so that would be value in the real world, not
Yes.
necessarily in the simulator.
Ah, true. That's absolutely right. So to deal with the mismatch between the simulator and the world, you're right. This should be the value in the real world of the current best policy. Right. But note that the classic exploration versus exploitation problem does not apply. Right? I mean, we need exploration in a different sense. We need exploration in the sense that we need to, excite all the states so that we can come up with a good reaction in all parts of the state space. But it doesn't hurt when the robot messes up. And so that is a much weaker notion of exploration and exploitation. There's no need for exploitation, actually. Maybe that's the way to think about it. Okay, so good. So one way to solve a problem down here would be RL and simulation, classical engineering. I would argue that the move toward like alpha zero and mu zero, what we're doing is we're actually able to solve more general kinds of problems, maybe some more general problems by searching online instead of compiling exactly everything. I will take a detour and now talk briefly about a system that I have worked on, which I think is pretty far over here on the right. It's kind of classical AI strategy where there's no machine learning at all, but it's pretty general. But I want to take a detour here and talk a little bit about contrasting two approaches, right? So these are both approaches to problems where we pretty much know everything about what's going on. So the left-hand side is the kind of offline RL strategy. And on the right-hand side is like the extreme alternative where we don't do any learning offline or online. An engineer designs a system and then the system behaves. And I just want to for a minute look at what the ingredients are in both cases. Like, what is the engineering work you have to do? Because in both cases, there's definitely engineering work. So one thing is, in the RL in the factory approach, we have to supply reward. In my kind of approach, you have to specify a goal. And just for a minute, I want to pick on MetaWorld, not for too long. But so here's a nice array of tasks for a robot to possibly perform in the world. But if you, like, I went and looked at the reward function for the pick and place task, and this is it. And I spent some time trying to figure out what that actually encoded. And it's a state machine. So the reward function in that case is not a function, it's actually a state machine. And it is very close to a program for solving the problem. Not quite. And I think it's possible that it's almost possible that doing gradient descent on the reward function would actually be not a terrible policy. Okay, so that means an engineer had to work an engineer worked really hard to do this. And there's nothing wrong with that, but it was work, right? Alternatively, at least in our planner, for that same exact problem, to specify the goal is easy. All I have to do is say, I want the target object to be at this pose. Okay, so am I being fair? Maybe not. Let's keep going. So another thing that we need is the Urdf. So that's just a declarative description of the dynamics of the kinematics and the shape of the robot and of the objects that are in the world. So in the RL in the factory approach, you need all that to build the simulator. In my approach, I need it to put into the planner. The RL in the factory needs a physics model in order to make simulator. I need these other things, operator descriptions, and I'm going to talk some more about that. So I basically need to build a formulation. I need to build a way of thinking about the problem so that the planner can work reasonably efficiently and effectively. So let me talk about that just a little bit. So if I could be standing up here and saying, oh, planning is awesome. You should really just do planning. But you can't, it's not that simple. If you tried to do planning in the space of like incremental joint torques, that would be a disaster because the horizon would be really long. And basically, as soon as the horizon gets long, nobody, I think, can win. And so I want to talk about building an abstract model for, in this case, robot manipulation planning. And in particular, we're going to think about an action space that's compositional, right? So that it can solve a very big space of problems, and that's lifted. Lifted means kind of first order, that it's described in a way that's independent of the particular objects that you have in the world, but instead in terms of their properties and relations. And what I hope to do by building this abstraction is to make things more computationally efficient. I will necessarily make the solution slightly worse or somewhat worse, because that's what happens when you make an abstraction, right? You have to give up something, but we hope that it will help. And so I'm going to tell you about an abstraction. And this is a very beautiful abstraction, I think, for solving, in particular, robot manipulation problems, called multimodal motion planning. So imagine that we have a world where there's a robot and a bunch of physical objects. And for right now, let's assume that the objects are rigid. I mean, I know that this thing can be extended, but let's imagine now that we have rigid objects or kinematic objects like doors and drawers, things that are jointed in a way that we understand. And so a state of the world then is the robot's configuration and the position and orientation of all the objects in the world. And a mode, so there's an idea of a mode. And basically, you can think about it this way. When the robot moves its joints, what state variables in the world change? So if I'm in free space mode, I can move my joints, and the only state variables that change are my joints. But if I'm in the mode of holding this pencil, now when I move my joints, I change the pose of the pencil. Or if I'm up against something and I poke like that, maybe I change its position and so on. So a mode is, in some sense, a smooth dynamics involving a subset of all this enormous set of state variables, right? So I'm in a house, in a world, think of all the state variables, there's 100,000 state variables, but really at any given moment, I can't affect very many of them. So I think of planning in some sense in terms of going between modes and moving within modes. And let me just show you a picture. The picture is better than all this talking. So let me just kind of talk you through this. This is actually an old idea due to Hauser and Latome. I put this picture in here because I like the picture. It's from a newer paper. So let's just look at this green manifold for a minute. Okay, so imagine the whole state space is my joint angles plus the poses of all the objects in my house. So that's a really big state space, like a really, really big state space. And this green manifold here is like my current, you can think, well, all the positions of all the objects in my house right now, they're static, and I can move my limbs. So I can move in this very small submanifold of the whole big space. That's the green manifold. But if I manage to get my fingers around the pencil, now I can suddenly move in a different manifold. And that's the manifold where I'm moving and the pencil's moving, but the pencil is actually constrained relative to my fingers. And so you can think of that as like the pink manifold. So the intersection of the green manifold and the pink manifold was right the moment when I was able to grab the pencil. So this gives us a kind of a really nice way of thinking about planning and building models that's kind of elegant and efficient. And so what we did is we took the multimodal motion planning framework, which we've been working in basically, and framed a set of mode families, right? So there's moving through space. There's, generally speaking, picking up an object and moving while holding it and putting it back down. There's touching and pushing an object. And there's grasping and operating, means moving a kinematic thing like a handle or a drawer. So we built a planner that does multimodal motion planning, and we read in the URDF files from the meta world problems. And we read the reward functions and extracted the goal for each of them. And we solved a whole bunch of these problems. So, and without any learning, so zero learning, right? One planner, zero learning, solved all these problems, did not solve all of them. Some of them need another mode. Some of them take advantage of the physics of Mujoko, which is not the physics of the physical world. So objects can kind of interpenetrate. So there's some like slightly funny stuff going on in a couple of those examples. But the point here just a little bit is that with really pretty general code, we were able to solve a lot of these problems just directly. Okay, so now what I want to do is think about, how can we solve more complicated problems, and then eventually how can we learn more of these pieces and parts, because I don't believe that I can engineer the whole thing. I think I'm going to skip this. We have an awesome robot. Now we'll watch it do some stuff. Okay, actually, let me stop for a second. So this is now real robot doing things. Completely hand-built. There's nothing in here that's learned at all. The goal specifications are quite general. It's basically using a version of multimodal motion planning. Any given thing you see this robot do, a few bright undergraduates could have made it do better with 2 weeks of planning, 2 weeks of coding. But the same code is going to do all these things. And that's what I think is important. So here, one sec, I just want to get the video to play. There we go. Okay, so here we asked the robot to put the blue box where that can is, and it saw the can in the way, and it moved it out of the way, and it put the blue box where it needs to go. Here we asked it to move the green box to the edge of the table. The green box is too big to pick up, so it figures it has to push it. It figured it had to move the orange thing out of the way. It knows its pushing is not very reliable, and so it keeps looking to see if the object went to where it was supposed to go, and shoves it until it gets where it's supposed to be. In this one, we asked it to just go out of the room, but it knows that it can't move through space unless it's sure that that it's free. So it looked and it saw these chairs in the way. And so now it is planning to move the chairs out of the way. It moves one chair out, it grabs the next chair, and then it just decides to take it with it, because we only told the robot to go out of the room. We didn't tell it about the chairs. So it went out of the room with the chairs. Here we asked it to put a full oil bottle on the other table. It's picking up the oil bottles to see which one is heavy and not, and so on. So the point about this is that it's pretty general. Okay, so now let's think about learning, right? And so far I've spent all my time really talking about problems where the engineers knew a lot about the domain where the robot was supposed to work. What happens when the engineers don't know so much about the domain where the robot's supposed to work? And so there's reinforcement learning in the wild, right? So this is the case where, like, okay, you put the robot in my house and it has to learn how to do stuff. And I guess I would argue that you have to be careful about that, because you don't want a robot learning physics in your kitchen, I think.
Leslie, may I interrupt for a second?
Sure.
Tell me if this is not the perfect time, but there are 2 questions that have been sitting in the Q&A, and I might actually have an extra one as well.
Sure, happy to.
So Pierre Fournier was asking about the modes that you defined. Are these modes related to the idea of sensory motor contingencies in developmental psychology? So really making
wow. That's a great question. I don't actually know. I mean, I think the easiest way to think about them is that they involve sort of regimes of dynamics that are smooth. So if you think about the dynamics of me coupled with the world, it's hybrid in the sense that there are discrete, discontinuous switches between relatively smooth kind of dynamical systems. So when I change my contact interaction with something, for instance, I kind of change the regime of dynamics that I'm in. And that's the basic idea.
So if I may rephrase, because I had a very similar question. So to me, that sounds like those are closer in sense to the options, for example, that we define in hierarchical reinforcement learning, or the hierarchies in hierarchical planning, as you've shown. They're actually rather closer than those to those, sorry, than to behaviors in the behavioral space, just for example, as defined in goal exploration processes. So that they're closer to temporal abstractions than to goals. Sorry, making that shorter.
Good. Well, okay, so first let's just make the connection to hierarchical reinforcement learning. I think that this is like, as you know, when you try to make a hierarchy, there's some hierarchies that are virtuous and other ones that really aren't, like they just don't work out. And what you're hoping when you're making something like options is that there will be beautiful little policies at the lower level that are smooth and compact and you can reuse them and so on. And I guess in that sense, the idea that moving within a mode is amenable to a beautiful, compact, smooth policy, I think that that's like a really good analogy. And the way we use these things is, in fact, the planner operates in terms of goals at the high level, but then it executes controllers that are policies that move through the modes and change modes. So basically each operation at the high level is either a mode switch or a moving through smoothly through this lower dimensional manifold.
Sure. Thanks. There's a second question there that's asking, could you share not just the complexity, but the amount of code needed for the planning agent that solves 43 out of the 50 tasks? And for example, is it simple but vast amounts of code? And maybe a related question, which I saw somewhere else, is for the video that you just showed of the PR2 robot moving around, how are the goals specified actually? Are they given as general modes actually? Are they goals, or is there a reward function behind it? Like, how complex is it to engineer?
Good. So in terms of the amount of code, there's a general purpose planner, which is basically the same one we used for MetaWorld as we used for the PR2, as other people use for all kinds of other things. So it's not necessarily a simple piece of software, but it's a very domain independent piece of software. So, and it's not as domain independent as I wish it were at the moment, but it could be made more so. So it's definitely a carefully engineered artifact. Lines of code, I have no idea. I mean, it's a hell of a lot simpler than, like, say, TensorFlow. But you should think of it like that, I think. You should think of it like a general tool. To solve these particular problems, we probably had to define these modes, to talk about pick and place. That's probably, I don't know, a few pages of code, like not a ton. Like, to describe pick is like this much and place is like that much. And then we need some samplers. So I don't know, it's not a vast amount of code. Then the question was, I'm sorry, there was a question about the PR2. Tell me again what that was.
Oh, that was sort of related, but that's actually sort of related to the last question in the Q&A right now. So let me move on to this one. We'll actually catch up.
Okay.
That question says, in the context where a robot has to learn a new task, and this task requires the success of many sequential actions, and at the end gets the outcome, whether the task was successful or not, how do we choose a good reward function to represent the success of a trial? So if I understand the question correctly, it's pretty much related to also how do you specify goals? How do you actually encode them? Which was pretty much the question for the PR2 robot.
Good. So the goals are straight up specified as an assertion in something resembling first order logic. Like, this object, you know, the apple is in the bucket, or there's a full oil bottle on the left-hand table. It's a declarative specification of the end state, full stop. There is no reward. There is no value function. There's just a goal. Yeah.
Thanks very much.
No trial.
Very, very strong link with classical AI representation.
Absolutely. That's right.
Okay. I suggest we move on, and maybe we'll get back to those questions if needed.
Awesome. Okay. Okay, so we're done with the robot. We're talking about learning. I was complaining about RL. Okay, so now I want to say, just to talk about the other regime of reinforcement learning that I think is interesting and important to think about, is the one where the agent is actually learning in its actual lifetime. And that's what RL was originally kind of formulated for. But I just want to say that if that's really what you're thinking about, like the agent is learning in the world, then the curves, the objective function is something really very different, right? And it should be, now the robot is interacting in the world and it's breaking things and getting hurt. And now it's no more the question of how good is the policy when we're done learning. The question is, how many dishes did you break? And you better be measuring cumulative reward from the first moment. So I think that this is a sensible setting to think about in some circumstances, although you have to be very careful. And the offline setting is sensible, but I would argue that many people right now in the reinforcement learning world are kind of mixing them a little bit, and they're not super clear exactly what the right objective is that they're pursuing. So I would just, that's just a little side note, but I'm going to zoom ahead because I have a couple more points I want to make. Okay. Yeah. Okay. So now I want to talk about basically, what can we learn? So let's say I'm this like old school person who hand built this thing and I have this architecture, but I understand that learning, I mean, I care a lot about learning and I think learning is important in a bunch of different ways. So what I'm going to do now is just fly through some places where we are injecting learning into our setting. So let me start with perception. This is actually something we're doing right at this very moment. And we have this project with a name that I like. It's called MOM, but it's M0M. So manipulation with zero models. So you could complain about the meta world stuff that we did, that, well, we had to read in the description of the objects. So how useful is that? Although again, in meta world, they have to read in the description of the objects to make the simulator. We had to read in the description of the objects to plan to manipulate them. But could we plan to manipulate objects that we have never seen before, right? So you could, right? If I put a bunch of random junk on a table and asked you to put all the blue ones in a basket, you could totally do that. So can we do that? So the question is, can we use perception to do that? So we're going to assume that we know the robot kinematics. Like I learned my kinematics personally a long time ago, and I don't have to relearn them every time I learn a new thing. So I'm going to assume I know my kinematics. And it's not that hard to learn kinematics if that's what you really want to learn once. And assume that we have, again, a multimodal model. And we're going to use perception, we're going to use raw input. So no built-in models of objects at all, but we're going to try to do class agnostic segmentation, a thing that predicts based on point clouds, maybe where it might be stable to grasp an object, something that tries to complete a point cloud so that you can have an idea, given that I saw something from this perspective, roughly what volume does it take? Because I need to reason about that so that I can plan to move it around. And we're doing some category detections just so that it's easier to specify goals. So we're not required. We could do what we're doing without any category detections. So I'm just going to show you, this is like a 1 minute movie here. So this is using pre-trained perceptual stuff and the planner. We give goals in this form. Actually, let me just stop this for a second. So the goals are written in first order logic, basically. Put all the objects in the bowl of the similar color. No learning, no additional learning. The only learning here is the perception. And so we just give the robot a goal and it does it. It makes a plan, it does replanning. You'll see that sometimes it screws up. That's not surprising. Here, put all the objects in the region of the opposite color. Oops, it missed. And then it decides it has to move the drill around a little bit to make room for the bowl. Okay, there, it didn't see the cup. It said, oh, snap, I have to move the cup over. Now I'll put the Cheez-It box where it needs to go. It is imperfect, but it is non-terrible as robots go. We can also do this sort of stuff in simulation. But the important thing is, it's very general. It's very general in terms of what you could ask it to do. There it figured, push the object out of the way so it could put the can in the region. Put the objects in the bowl on the shelf. It's doing planning, completely planning to decide what to do. Okay, so there's that. so that was about learning things that go in this box. And by establishing a semantics, right, like that, what we want to have come out of here is an actual kind of representation of objects and their properties and relations, it means that we know loss functions for the training of the perception modules. And we can do that in a way that's not end-to-end. Like, I'm not a fan of the giant end-to-end. I mean, I understand why you could love the end-to-end, but I also don't know how you get compositionality and good generalization out of that. So if you can do it, that's cool. But right now, I don't know how to do it. So instead, what I'm doing is saying what I want this S to be and using pre-trained modules to produce it, and then using the planner to decide what to do. But now let's imagine that we wanted to do something new. So I like to think about this as like, I don't know, if you had a 10-year-old kid in your house and you wanted to teach them a new thing, they would know their own kinematics and they would know really well how to pick things up and put them down and a whole bunch of stuff, but you might want to teach them a new skill. So if you look at robot learning right now, there's a lot of work on learning particular skills. And actually, I think this is where the kind of current RL methods shine, where they're appropriate, which is moving in a low dimensional mode, right? Cutting, pushing, stirring, pouring, throwing. Those are things where you need a closed loop, you need the reactions to be fast, where there's really a kind of a low dimensional and sort of smooth space that you're operating in. So I'm going to assume that someone else is already working on RL for specific subtasks, sub-policies. But what I want to think about is how could I take a learned policy and integrate it into my robot system? So here's an example. Imagine pouring, right? So to do a good job of pouring, you need a closed loop controller that you would have to tune up, probably using RL. But we can ask now, so let's say you train up a really good pouring policy and you say, here, Leslie, now I have a pouring policy for you. I would say, okay, I have to figure out how to integrate that into my overall system. And in particular, so I'm going to show you kind of how we do this, right? So I'm going to add like a piece of declarative description of my domain into my planner. I'm going to say, I have this thing I can do that can cause liquid to be someplace, and I'm going to do it by calling your pouring policy with maybe a gain parameter or some parameter. And there's going to be a bunch of preconditions. I'm going to say, well, there's some kind of gross precondition like the source container has to have some liquid in it. But there's all these continuous variables, like I'm holding the cup with some grasp, and the thing I'm pouring out of has a certain shape, and the thing I'm pouring into has some shape, and there's a relative pose between the two objects. And there's going to be a constraint, a relation that if it holds among all of these continuous variables, then the pouring will work well. And if it doesn't, then it won't. So we'll call this the precondition, right? So what are the circumstances? In old options terminology, this would be the initiation set in a sense, not exactly, but something like that. We call it the preimage of the result. So under what circumstances is it the case that if I were to execute this policy, this result would happen? That's what I want to learn, because if I know that, then I can use the pouring operation in my bigger context. I'm not going to go into detail here. We use GP regression to learn basically a score function, right? So we say, well, given all these continuous parameters, we can try pouring in all these different kinds of situations, and we can measure like what percentage of the particles actually end up in the cup. And so that's a straight up regression problem. And we can do active learning so that we don't have to generate too many examples. And this part doesn't matter. I'm just going to skip it. Just to make a little point, it's not so easy to gather the training data to do this. And this is why we had to pick up a whole heck of a lot of beans off the floor. So it's good to be sample efficient. But the fact is now we can take the pour operation with the preimage that we learned, add it to the planner and to the domain descriptions that we had before for picking and placing, give the robot, put objects on the table however we want to, give the robot a general goal, and it will do what it needs to do. Like it moved the green box out of the way so that it could pick up the cup, so that it could come over here and pour. Or in a minute, there's this is not the best example. The next example has something good that I want to talk about. So in the next example, the bowl is all the way over there where it can't reach to pour into. So it reasons on its own that what it should do is push the bowl over into the space where it could reach to do the pouring. So again, this is pretty general behavior. There's no reward functions. It just learned the preimage of the pouring operation and the pushing operation, and all the rest of this is planning. And in this case, it knows the object models. You could combine this with the previous thing, but we haven't done that yet. Oh yeah, there's a fancy neural network learning story that I'm not going to tell you about. Another kind of thing that we can learn. Okay, so everyone loves AlphaZero and so on. And what is that about? That's learning search control knowledge, right? That's like saying, oh, I have a planner for playing Go or chess or whatever. But, oh, it's very, very inefficient because I have to search this giant space. And so it's very helpful if I can learn some policies or value functions, not because they're necessarily good enough to execute, although, of course, I understand now in AlphaZero, they're very, very good. But for us, we want to think about learning some, again, similar idea, learning partial policies or partial value functions that can help us in our search. So for one kind of part of planning, of multimodal planning, basically, you can think of the search space as picking discrete actions, basically picking modes, like I'm going to push object A or pick up object C, and then picking continuous parameter values that parameterize exactly how we're going to pick the thing up or exactly where we're going to push it to or place it. So we have a ginormous search space that kind of alternates between discrete and continuous choices. And another thing about this search is that the node expansions are very expensive, right? So in a game, the search is not terrible in the following sense, which is that if you're in a certain board state and you decide to take an action, it's really quick to compute the next state. For us, if our actions are things like push this object using these parameters, we actually have to do some motion planning to figure out whether that's a feasible thing to do and so on. So the node expansions even themselves are very expensive, and that modifies the way we think about the search. But what we're trying to do now is learn search control. And we're going to try to learn it at the discrete choice level. So at the choice of which actions to perform at the high level, which mode switches on which objects. And we would like to have aggressive generalization. So we would like the robot to be able to learn from moving these big boxes around in the apartment to apply its knowledge to moving objects around in these shelves. And so what we're going to do is learn a kind of Q function at the level of abstract actions of the discrete choices. And the hope is that we can, reduce the effective branching factor a lot. And we had this idea that maybe the abstract action values would generalize well. And there's a detailed story about using graph neural networks. So one thing is, if you look at these domains, every single problem instance has a different number of objects. So you need some strategy for being able to handle, kind of relational domain descriptions. So here we're using graph neural networks, where the relations on the arcs and the properties are actually, they were hand designed. They're relations like, is this object in the way of, there's individual properties, but the relations, the important relations are things like, does this object occlude my ability to manipulate this other one? So these relations we actually have to compute using a planner. So again, we're using the planner to put values on the arcs of the graph neural network. And then we do some typical kind of parameter estimation and some message passing to infer this kind of relational Q value. But we can use that now as search control to help the robot decide which objects to consider moving out of the way if it's trying to go somewhere or move some object. And loss function, and it gets better, right? Okay, but what's interesting is that we can train it on the apartment only, moving one object, and it can actually help with learning in the cupboard. Okay, so I'm going to do some conclusions and stop because I like having conversation. The conclusions here, the joke here is that I gave a talk a long time ago, and this is my conclusion slide from that talk, amended a little bit. So at that time I said, oh yeah, there's been a lot of progress in algorithms for supervised reinforcement learning. That's true. And I think now what can we say? Well, it's still true, but it's like really, really super much true. So I gave this talk originally the last time neural networks were cool, right? So they've been cool 3 times. So I would say this is the 3rd time. So the second time they were cool, it seemed really promising, and then it kind of fizzled. But maybe this time, I think probably this time it won't completely fizzle out. But I wanted to say that this doesn't directly give us solutions for building autonomous agents. And I think, maybe it now gives us solutions for generating some kinds of autonomous agents, but not really general ones. I still think we need human insight to complement the strengths of learning algorithms. And in particular, now I'm thinking more and more about algorithmic and structural biases. So these ideas of things like that you could do some amount of planning instead of just learning the policy, or that maybe the multimodal structure is a good one to try to in some way build in. So good. So I've done this work with my colleague Tomas and a bunch of students in our group. And you can watch the robot make some errors, and I'm happy to take questions.
Thanks very much, Leslie. While the questions are coming in, I already have a couple of them. One that was asked in the chat is that, in a way, pouring sort of requires a measure of task similarity. If you try to learn pouring milk into a jar in your kitchen, and you want to reuse that as a macro action or as a generic policy that I provide you or that you provide me with, and try to do that in another kitchen, that supposes that the two MDPs, the two worlds, the 2 environments we're interacting with are similar enough so that the policy is applicable. So instead of really having strong prerequisites or preconditions for such macro actions or for such pre-provided policies, isn't that more a question of task similarity, and how do you measure that in practice? Like, for example, on the robot you were showing just now, like how far can we go from the original setup that we can still use the pouring policy for the glass, for instance? Right.
So I think, again, like if I were, in our case, our pouring policy is really just a kind of a risk trajectory. So it's not even a nice feedback loop. Really, pouring should be a feedback loop where you're watching how much stuff you're getting in and you're trying to see if it's getting turbulent and so on. So, and there's a bunch of people who've worked on that. But the thing is that the policy, so here's the cool thing, I think, is that I can make the lives of reinforcement learning people easier in a way by only asking for the RL to solve a smallish subproblem, right? So the RL doesn't have to figure out how to grasp the cup. It doesn't have to figure out where to put the other cup. It just has to control the pouring process, right? And so if I were training like a better controller for pouring than the one we have, which really just rotates the wrist, I would set up an RL problem, maybe with lots of different cups and lots of different kinds of liquid, and I would train something general, right? So the point is, it needs to be conditioned on properties of the world and work in reasonably general circumstances, or I'm just not interested in it. This is why I think the idea of a task is actually harmful.
Indeed. So I'll just pick up questions from the list of Q&As. How does the robot learn not to turn the glass over, which would empty the glass before the pouring action could take place during manipulation? So.
That's a great question. The answer is, in this case, we programmed it to, if it was holding something, to not change the orientation. How would it learn that? That's a super good question, and I love it. So the way to think about that is that there is a mode. There's a mode that involves the robot and the cup and the stuff in the cup. And if you want to stay in the mode where the stuff is in the cup, you need a mode controller, which is a little bit not the same as the mode controller for just moving in free space any way you want to. And so I think it would be, again, like a totally reasonable, well-formed machine learning problem, if you wanted to learn it, to say, how can I move so that the stuff won't come out of the cup? So right now we do it just kinematically. I mean, we just reason about the cup staying upright, but actually it's more complicated than that, right? Because it depends on how full the cup should depend on how full the cup is and involve the acceleration and how viscous the stuff is that's in there. And so totally, this is where I would want to use RL. I would want to use RL to learn a general strategy, maybe, for moving the robot while it's holding something with stuff in it. But then I would want to use my planner to put that together with everything else.
Sure. Another question, is it possible to use natural language as prior knowledge for easier creation of the planner and cause-consequence relationships? I guess there were a couple of other questions in that line. Let's just answer this one.
Yeah, no, I think that's right. And in fact, we're kind of in the middle of writing a proposal that kind of goes along, I don't know, maybe not exactly natural language. When I do stuff, I do it with like formal language. Not because I think humans should write down formal language, but just because I think the problem of translating from natural language to some formal language might be somewhat separable. And so I'm just not getting engaged in that. But no, the way I want to think about teaching this robot to do something is the way I want to think about teaching a 10-year-old. So I could teach a 10-year-old to solder or to beat eggs or to do some new thing. And how would that go? And you would say, this is what it looks like when the soldering has been successful. You know, look, the bead is like shiny and not lumpy. Or the eggs are whipped in a nice way because they're kind of frothy, but not coming out of the bowl or something, right? And so, and you might give a demonstration, maybe two, not more. And you might give some guidance about what to pay attention to. And so yeah, no, I think that's a good idea.
Definitely. So if I may, that strongly relates also to what you were saying earlier about reducing the amount of human engineering or balancing it with the amount of machine search or machine learning overall. So right. Definitely a couple of demonstrations would make sense, probably not really more than those.
Right. And that would be like in the wild. Like you could, in the factory, if you had to, right? If you were making really awesome home robots, you know, you could spend 5 or 10 years in R&D in the factory, and you could have a lot of demonstrations if you wanted to, but you still have to pay for them, right? I mean, and you still have to decide whether, you know, you wanted to spend your budget on that versus whatever else.
Sure. Here's a rather long question. I'm not sure I read it properly before passing it to you. So, would you say that reinforcement learning could be, on the one hand, a generalized approach to explore more widely and more exhaustively a space of alternatives that we still have to structure using our preferred model and categories? And on the other hand, an approach to optimize and robustify our models and structure with respect to the noise and things that we don't know how to model correctly? Sorry, if you want
okay, yeah, no, good. So that was a whole lot of things packed in.
Yeah.
I will give some pieces of answer. So is reinforcement learning a good strategy for exploring? And I would say, I don't know why it would be. Like, if exploring is what you want to do, you should make algorithms for exploring. So I think RL is super attractive. It's a beautiful thing, and it's partly what makes it attractive is that it sort of purports to solve the whole problem with one simple mechanism. And it's romantic, I think, and very attractive to imagine that we could solve the whole problem with one simple mechanism. But I kind of just, I mean, I worked in reinforcement learning and eventually decided that I didn't, at least maybe I just have a small brain. I'm willing to admit that. I can't see how to get from what RL can do to where I want to be. Um, uh, and it's not an in principle argument, right? Because in principle, if with enough training and enough data and a hairy enough simulator, you can learn to do anything. But the amount of training and data, I think it might just be inconceivably big. But I think that so there was a question about exploration. I think if what you want to do is exploration, you should just say, I need to think about exploration and try to make something that does exploration, and not necessarily make that be the same thing that's also doing planning and also doing estimation and also doing all these other things. I'm just not sure that it's useful to mix all that stuff together. I do think that, again, like handling real world noise. Well, so one thing is, I think it's popular to imagine that planning related approaches have to have perfect models, but I hope I've shown you that that's not true. That by wrapping a loop around the planning on the outside, what a control person would call model predictive control, kind of like, we can screw up. It's okay. We drop things, we pick them up again. We get a wrong perception. It's okay. It just keeps, the robot just keeps trying. And so you can just keep trying. And that's one way to deal with noise. You can make better estimation procedures, right? So another way to deal with noise is to use, let's say, trained vision algorithms. Another way to deal with noise is to make your local controllers be nice closed loop feedback controllers, which maybe you acquire using control theory, or maybe you acquire using RL.
And maybe that's kind of a follow-up question on that. Gabriele says, I see the strong points of this approach. So I assume the compositional approach of using planning and hierarchical planning for solving larger tasks. But I think I'm missing a bit the weaknesses. Can you please give us some insights on those?
Good. So what are the weaknesses are right now? I have to understand. So, well, it depends whether, I don't know if this is a weakness or not, but it's certainly a fact which many people would take to be a weakness, is that my system that I'm building is about a robot in the physical world. It has built into it absolutely at its core that I live in three-dimensional space, that I'm manipulating objects, that, so this isn't I couldn't take my same algorithms and use them to, I mean, directly to, I don't know, control a factory or place ads on Amazon. Or so one again, a thing I think that's virtuous and attractive about the general RL framework is that you can take your favorite policy learning algorithm and apply it to absolutely any domain in the whole world. I think that's, so it's at the tool level, it is super general. What I'm making is a thing that is less general at the tool level, but I think somehow it solves, but it's more general within this domain that I care about, which is the domain of interacting in the everyday 3D world with physical objects. So that's one thing. So there's a whole bunch of stuff that's just, I've just built in the idea that I'm a robot with kinematics. And another thing is, like, if to do a new problem, for me, it still requires some engineering. I mean, what we're interested in, I think if we can get the basic physical interactions down, picking up objects and placing them and so on, we can gradually add capacity, like the capacity to deal with non-rigid objects, or the capacity to solder, or the capacity to do these things. And I think we can develop a methodology for teaching these new skills, but I don't I haven't done that, and maybe it won't work. So I can't say for sure.
Thanks, Leslie. I guess we'll just have one last question. We're already over time, but this is very interesting, actually. So I'd like to keep on asking questions. So one last question. Can we use social learning theory in order to use robots' previous experience and improve robot performance in unknown environments and new domains and learn new tasks from previous ones? So a very generic question, but specifically on social learning theory.
So I think I don't exactly know what social learning theory is, so I have a little problem with that, maybe. I mean, I think that certainly we can learn by watching humans to some degree, and we can be taught by humans. I think we have to work that out. And I think robots could, they could all beam their experience up to the home factory, and we could try to figure out maybe I think we could do something where we build an aggregate prior that helps a new robot learn a new thing better. I think that could work too. But I'm sorry that if I'm not responsive because I don't know what social learning theory is exactly.